Hello guys, welcome to my YouTube channel. In this video, we will be discussing the mechanism for the formation of an acetal. So what is an acetal and how is one formed? Okay, what you need to first identify is a carbon that has a double bond to an oxygen, so either a ketone or an aldehyde group. Right here we have a ketone because this carbon is connected to two other carbon groups. If we had instead this, well, this would be an aldehyde. And if a ketone or an aldehyde is reacted with excess alcohol, or even just two equivalents of alcohol, in the presence of acid, so acid is H+, what happens is the carbon, I'll label the carbon in purple, that initially was double bonded to an oxygen, in the product, in the acetal form, the same carbon will now be bonded to two OR groups via single bonds. So this would be an acetal. So yeah, I guess we could just guess the products, but OChem is all about the electrons. So we've got to go and look at how this happens, aka let's do the mechanism. Now, the mechanism for the formation of an acetal can be broken into two parts. Part one is the formation of a hemiacetal. I'll get to explaining what this is. And part two is the formation of the actual acetal. But now, part one is broken up into three steps itself, A, B, and C. Step number one is a proton transfer. Step number two is nucleophilic attack. And step number three will be another proton transfer. A way to remember this is, you know, the song TNT, dynamite. Here you can instead say PNP, you know, like for TNT, but PNP, where the P is proton transfer for step A. The N is nucleophilic attack. And then the third P for P in PNP is just another proton transfer. Step two can be broken up into four steps. Step one is a proton transfer. Step two is the loss of a leaving group. Step three is nucleophilic attack. And step D is proton transfer. Now, the way I memorized this when I was in second year organic chemistry was via the acronym Pablo, left, no, potatoes. Where P in Pablo is for proton transfer, L in left is for loss of a leaving group, no is for nucleophilic attack, and then potatoes is for P, another proton transfer. So without further ado, let's do an actual example, but I want you to remember what we just went over. Write it down, have it beside you as we go through this problem, because I will be constantly referring to these two parts, which are broken into part one, 3 steps, and part two, 4 steps. All right, so let's say the question says, draw a plausible mechanism for the following transformation. So, can I identify a ketone or aldehyde? Yes. Okay, so we know this carbon is the carbon that is going to change. And now the product is our acetal, so we have that same carbon, but now it has two single bonds to two OR groups, OR, OR, where the OR is whatever alcohol was thrown into the reaction. Here it was ethanol. So that's why we have two OET groups attached to the carbon that initially had the ketone. But now they also give us another hint with respect to the mechanism. Well, they tell us that water is our leaving group. So going back to step 2 of the mechanism, part B, we need to lose a leaving group. So we know that leaving group has to be H2O. Okay, they tell us this. Yay. So let's go through the mechanism, starting with part 1, which is broken up into 3 parts, like I said previously. So I'm just going to put these 3 parts of part 1 in the top left-hand corner. So we will refer to it as we go through part 1 of the mechanism. Holy, that is a mouthful. Part A of part 1 is a proton transfer. And first thing we got to understand is that there's 2 general types of reactions. There is either acid-base reactions, or there is nucleophilic electrophilic reactions. But acid-base reactions are much faster because they're just exchanging a hydrogen, generally, if we're talking about Bronsted-Lowry. So if I had to choose between an acid-base reaction happening first or a nucleophile-electrophile reaction occurring, I'm going to go with the acid-base reaction. They are always at play and they're very, very, very fast. So, what two species would be involved in the acid-base reaction? Well, we have H2SO4, a really good acid, and we have ethanol, a really good base. That means the first thing that's going to happen is that H2SO4 is going to react with the ethanol, because this oxygen has two sets of lone pairs, and one of the lone pairs can be used to go snag one of the acidic hydrogens. 2 in, 2 up. So you get this equilibrium where you have an O minus and then plus an O that has two hydrogens. Oh no, it's positively charged. Yes. Therefore, this is going to be our proton source. So we've just generated the proton source for the what? Oh, we can now get to part A, the proton transfer, which is going to involve our starting material and the protonated form of the alcohol. So now we are starting step 1A. So if the goal is to transfer a proton, I need somebody to take a proton and I need somebody to lose a proton. That is what a proton transfer is. So this oxygen has two lone pairs. Let's put them in pink. And this oxygen right now is fairly happy. It is neutral. But this oxygen, the oxygen in green, is very, very sad. It has a positive charge. And since oxygen is an electronegative atom, that means it doesn't want to be positively charged. So what does it want? Well, it wants to gain back a lone pair so it can be neutral. So this oxygen is going to steal a hydrogen, 2 in, 2 up, so that oxygen can gain back a lone pair and become neutral. This is step 1. This is our proton transfer step. Everything here stays the same, except one of those lone pairs now exists in a bond to the hydrogen that was stolen. And now this oxygen is positively charged, whereas the green oxygen is now neutral. This is the outcome of step number 1. Now this oxygen is happy, but now this oxygen is sad. So let's go to step 2. Step 2 is nucleophilic attack. Our nucleophile is going to be the alcohol. Who's it going to attack? Well, is it going to attack the oxygen directly? Never, 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 never. Who it's going to attack is always the carbonyl carbon. I hope you're picking up on the trend of organic chemistry too. We're usually attacking the carbonyl carbon. So one of these lone pairs is going to go 2 in. And then 2 electrons in one of the bonds is going to go 2 up. So the pink oxygen can gain 2 electrons, so gain a lone pair, and become neutral again. This is going to be the product of step 2, the product of the nucleophilic attack. Bond to the green oxygen, which still is bonded to 1 hydrogen, still has the green lone pair. Oops, but now it's positively charged. So it's unhappy now. It seems like we're always going between happy and sad, happy and sad. Yes, that's the idea here. But almost at the end of part 1, all that's left is a proton transfer. Identify the unhappy atom. Here, the unhappy atom is the oxygen. And that is the exact atom that is going to lose a proton. So in order to become happy, the green oxygen must now lose a hydrogen. Well, who's going to steal that hydrogen? Another alcohol group, because it said in the question that the alcohol was in excess. And the alcohol is a base. Bases like hydrogens. 2 in, 2 up. The green oxygen gains back a lone pair, becomes neutral. This would be the result of finishing part C, which is the final proton transfer. So going back to the very beginning of part 1, we have a proton transfer. This is part A. Then we have nucleophilic attack, that is part B. And then we have another proton transfer, part C. And what do we get? We get our hemiacetal, which is the point of part 1, the formation of the hemiacetal. Boom! So now all we got to do is step 2, which is the formation of the acetal. So taking your hemiacetal that you just worked hard to form, now we got to go through 4 steps in order to form the final acetal. So now, part B of part 2 is the loss of a leaving group, and we already established that we're going to lose water. So if water is our leaving group, how could we achieve this? Well, first of all, we need to form an OH2 plus species, And then this group will leave into the abyss. So since part A is a proton transfer, who's going to grab a proton? Well, since we want to produce H2O plus, the OH group has got to grab that proton. Who is it going to grab a proton from? Well, remember, this guy grabbed a proton. Another alcohol became protonated. So we have a proton source, O plus. So this O is going to take one of its lone pairs and go 2 in, 2 up onto the oxygen. And what do we get? We get our leaving group. We get an OH2 plus. The purple lone pair is now involved in a bond to a hydrogen, and this oxygen becomes positively charged. Ah, that's our leaving group, yes. So we just finished the proton transfer step, part A. So now we need to lose H2O. Before I show you how to do this, I'm going to tell you a fact. Well, let's go through a little bit of a story. What's easier, to change your own shirt or have somebody else change your shirt for you? Well, depending on the situation, it would be probably faster if you changed your own shirt. We're going to call this intramolecular. And intramolecular, which is changing your own shirt, in comparison to intermolecular, which would be if somebody else changed your shirt. Intramolecular is much faster than intermolecular. It's faster to change your own shirt than it is to have somebody change your shirt for you. And you might be like, how does this apply to OChem? Well, intramolecular reactions are much faster than inter. That's the moral of this story, and hopefully it was so annoying it sticks with you. So intramolecular reactions are faster than intermolecular reactions. So therefore, we can lose this leaving group via 2 in, 2 out. That's an intramolecular reaction because nothing from the outside is pushing off the leaving group. A group within the structure is pushing off the leaving group. That is intramolecular. So what is the product of part B, which is the loss of our leaving group? Copy, paste the whole thing, erase the water because it went away. So we get an OH2 and we get H2O into the abyss. And now one of the lone pairs becomes an additional bond. Let's straighten this out a little bit. And this green oxygen becomes positively charged. Oh no, so now it's unhappy again. So what's step C? Well, step C is nucleophilic attack. And what do we want to achieve in the end? Well, we want this carbon, the blue carbon, to have 2 single bonds to 2 OR groups. So who's going to be your nucleophile? It's got to be the alcohol. You need one more alcohol in your product attached to this carbon. So therefore, your nucleophile has to be the alcohol. I'm just going to copy and paste this onto a different page. So we have alcohol in solution, OH, ethyl group. This O has 2 lone pairs. One of the lone pairs can go bada bing, 2 in. And then bada bing, 2 up. We now have a single bond to the green oxygen, which has 1 green lone pair. Now it has a purple lone pair. And it's connected to a CH2, which is connected to a CH3. And now we have another single bond in blue to the white oxygen that's still connected to a hydrogen and also connected to an ethyl group. But this oxygen is positively charged. And going back to our 4 steps, well, we just completed part number C, which was nucleophilic attack, right? So what's our final step? Our final step is a proton transfer. So who's unhappy? Identify the person that's unhappy. This oxygen is unhappy. Now the result of a proton transfer would be making this atom happy. So how does this oxygen become happy? Well, it needs to gain a lone pair. Therefore, a base, an alcohol, is going to come and steal this hydrogen 2 in, 2 up. That's the result of a proton transfer. That is a proton transfer. And we get our final product, which is our acetal. 2 lone pairs, 2 lone pairs. And that is our acetal. All right, guys. I hope this video was helpful. I hope you learned something and had a little bit of fun. Maybe you like chemistry a little bit more than you did before you clicked on this video. That would be great. Please make sure to leave a like, comment, save, and/or subscribe to my channel if you like my content and you find it helpful. Your comments mean the utmost to me. They always make my day, and literally whenever I get a comment from you guys, I'm smiling the entire day. So please, if you have something to say, let me know. I always reply to the comments. Have a great day. Bye.